All right, we're working on break challenge number 3 here. And so we need to implement this find primes function according to its docstring, which is provided for us. So we're going to take a list of integers and return a list of all of the primes found in that list of integers. And so essentially what we're going to do is implement a filter accumulator, right? We're taking a list of numbers and we're filtering out all of the numbers that are not prime. And then just returning a list of all of the prime numbers, found in that list. All right, so I'm going to jump over to VS Code, and we're just going to go ahead and implement kind of a bog standard accumulator pattern. So primes, empty list, and for num in num list, basically we just want to append num to primes if num is prime itself. So if num is prime, then primes.append num, and then finally we'll return our list of primes. So now, I mean, this is the core logic is done. We just need to implement this, whatever this is, this Boolean check right here that checks if the number is prime. And the way we're going to do that is by writing a helper function called, not surprisingly, is prime. And so we're going to pass a number into this function, and this function is going to return true or false. And so we can directly use it in this if statement. And yeah, so let's go ahead and implement that. So is prime num. And we're going to get our freebies out of the way. So if num is equal to 2, we can just immediately return true. If num is equal to 1 or num is even, we can immediately return false. And the reason I'm kind of putting these here, this first sort of branching statement, is because it's going to knock out a lot of cases for us immediately without us having to jump into the much more expensive and more time consuming process called trial division. So in trial division, what we have to do is for I in a range of numbers, we have to check if num mod I equals 0, and I guess first I need to make a prime flag. So this is a Boolean flag here. I'm going to start it out as true. And then for I in some range of numbers, I haven't put that in yet, we're going to check every single one of those I values in that range. We're going to see if it's a divisor of num. And by doing the way that we do that is by checking if num mod I is equal to 0. And if that is true, or if that is the case, then prime is false. It's not a prime number. So we can set that flag to false. All right. And now I need to fill in this range logic here. So, right, we're checking num mod I for I in this range here. So we don't want I to be 1, right? Because num mod 1, no matter what num is, anything mod 1 is always going to be 0 because everything is divisible by 1. And that's not helpful to us. We don't also want to check I equals 2, right? Because we're already doing that right here. So that's just a wasted computation. We don't need to do that because, this condition num mod 2 equals 0 if I is equal to 2, that's already being done here in this branch of this if statement. And so, yeah, I mean, it's just redundant. We don't need to do it again because this function is immediately going to return if that condition was already caught. So we don't even need to check it. So we don't need to start our range at 1. We don't need to start it at 2. We need to start our range at 3. And now we need to figure out where to go to. And this is a freebie from us, because we don't expect people to know this. So what we're going to do is go up to and include. So that's what I'm doing when I do +1 here. We're going up to and including the square root of num. And I'm not going to get into the number theory for why this is the smallest possible upper bound on this range that we can check in trial division. You'll just, we're just giving this to you as a freebie. This is an optimization. This is, again, this is the smallest upper bound of this range that we're performing trial division on. So this is kind of from 3 to this square root is the fewest numbers that we need to check in order to determine whether or not a number is prime. And then you'll notice I left a comma here, and that's because I'm going to make use of the step parameter as well. And so we're going to step by 2. And we're starting at 3, which means, the next iteration is going to be 5, and after that it's going to be a 7. So we're skipping all the even numbers. And the reason I'm doing that is because, well, if num mod 4 is equal to 0, then that means num mod 2 is also equal to 0, right? Yeah, so, and again, we're already taking care of that up here. Because I guess I should say, all even numbers are divisible by 2. That's what this statement is saying right here. All even numbers are divisible by 2. So I don't need to check any even numbers in this trial division, because if num is divisible by an even number, then it means it's also divisible by 2. And so that's redundant with this Boolean check right here. And that means that we can skip every other number in this entire range. And that halves the number of iterations that we have to do. Yeah, so kind of all of those things in combination end up making this the most optimal that we can sort of make this. We could make another optimization where we said if num is in a list of like the first couple of primes, 7, 11, 13, 17, on and on and on, we could, make this list as large as we can think, and then we would just start our range at whatever value is next, but that's kind of just getting a little bit silly. So we're just going to keep it at num equals 2 here, and then start our range at 3, step by 2, and then set this prime flag equal to false if we find a divisor. And then 8 minutes into the video, kind of buried the lead, we're going to use our break keyword here. So that's kind of the whole point of this video, and the whole point of this challenge is to figure out a way to use break. And that's how we're going to do it. So if we find a divisor, there's no point in checking any of the other numbers. We've already figured out that num is not prime if we found a divisor in this range. And so we can immediately break. And when we immediately break, we can immediately return whatever the value of prime flag is. And the reason I can do that is just because, well, if this for loop completes, then that means it was never broken out of early, and that means that prime flag was never switched to false, which means it's still true, and that is correct, right? If we complete this for loop and don't find any divisors, that means we've found a prime number. So yeah, if we do find a divisor, we'll set the flag to false and break. And if we don't find a divisor, we'll exit this for loop sort of gracefully, without having to break anything, and just return that prime flag. And that's the core logic for our function. And this is reusable, right? And that's why I broke it out into a helper function, is prime just kind of by itself, because then we can use it in other cases. I didn't want to bury this logic inside find primes, because then, it's not available. It's kind of buried inside of this more specialized function. So yeah, break it out into a helper function. We can test, well, I would suggest that your workflow include actually testing this function, although this is like my 10th take at this video, so I'm pretty confident that I've written it correctly here. What I'm going to do real quick here is actually show you the results of our isPrime function on some mind-bogglingly huge numbers. So I know this kind of just looks like a string of digits, but this is indeed an extremely large integer. And we're going to check if they're prime. And I guess first I'll say, well, none of these are 2. None of them are 1. And none of them are even. None of them end with an even number, which means none of them are divisible by 2. And so we know that this block right here for our freebies is going to get passed over for all 3 of those numbers, and we're going to have to jump into trial division, where we have to check every number in that range from 3 up to the square root of whatever this number is, or whatever the square root of this number is. And this being a very huge number, that means we're going to perform trial division for a very large number of numbers. And I just want to show you how fast this actually is going to be. That was pretty much instantaneous. You probably kind of missed it. That was so fast. And these are, again, huge numbers. That's 16 digits, I think. 15 selected. 15 digits. 14, 13. So, yeah, that's a lot of digits. You know, a billion has, 9 digits in it? 10 digits? So these are larger than a billion. That's it's kind of a mind-bogglingly huge number, and we checked its primality near instantaneously. And that's a very big deal, because checking the primality of extremely large numbers is an active area of research, having to do with encryption, for one thing. And yeah, we want to be able to check if a number is prime quickly. And yeah, I don't know, I could add another 2 digits in there, and this is going to be a little bit slower. Oh, actually, that happened to be very quick, just because I happened to pick something that isn't prime. I don't know if I'm going to be able to get lucky here, and you might be able to hear my fans in my computer spinning up, because now it's actually performing trial division on a number with 17 digits in it, and I happen to pick a prime number, yeah, with 17 digits. Massive, massive, massive number. And actually, what I want to do real quick, I might just be talking to my dog at this point, because I showed you all of the code. But if you're still here, I just want to show one little thing here. If we instead don't skip the even numbers, if we do all of those extra iterations, all of that wasted work, watch how much, you see how much slower that was? It's just because we're doing twice the amount of work. And then this one is kind of the kicker. If we were to instead maybe go, to num div 2, I don't even know if this is going to finish. I'm probably going to have to end the video before this ends, because that is so many more numbers that we have to do trial division on that are not necessary. So hopefully you're kind of getting the point, which is that, yeah, optimization is smart to do. And yeah, I guess while we're waiting for that to run, we can go ahead and just make sure that we're actually passing our tests. And yeah, we got it correct. So I guess we'll just see you in the next video, because that still has not finished. Still checking if that's prime. Yeah, so all right, see you in the next video.